Okay, let's do some torque examples. And this first one, at least the first part, will be very similar to another problem you've already seen. A 5-meter long, 30 kilogram seesaw has adjustable seats that can be slid forward or backward to accommodate different users. It is pivoted about its center of mass. A 25 kilogram child sits at one sits at one end of the seesaw. Where must a 500 Newton force be applied in order to hold the seesaw with the child horizontal in the air? That's the first thing that we have to do. So, in order to do this problem, let's start by making a sketch. Okay. Here's my fulcrum. Let's see here. We have, let's see. We have a 25 kilogram child which sits at one end of the seesaw, so I'm just going to draw that him over here, him or her. 25 kilograms. We want to know where a 500 Newton force would be placed in order to balance the seesaw. Now, we can make a pretty good guess that's going to have to be on the right-hand side of the fulcrum, okay, but we don't know exactly where, so that's why I drew it in as a dot. Okay, so our next step is going to be drawing the forces in. Well, we know that the 25 kilogram child is going to push downward on the seesaw with a force equal to the child's force of gravity, so I'm going to label that FG1. I guess I could just, no, FG1 is good. Moving to the right, I have an upward normal force from the fulcrum, and I also have a downward force of gravity from the seesaw itself. I'm going to call that FGB. And then I don't know where that 500 Newton force is going to go. And since I'm dealing with forces and torques, I'm going to put my axis in, standard XY, and we're just going to indicate, this is how I indicate that counterclockwise is positive, kind of a little counterclockwise arrow with a positive sign. Now, last time what we did is we just wrote out the net torque equation and we dove right into it, and then we substituted it in at the end. I'm going to show you another way that you could do this, which is writing out all the individual torques kind of off to the side. There are four possible forces here, so that means there are four forces, so there's four possible torques. We're going to see what each of them is equal to. We're going to start, we'll go left to right. So let's start with the torque from the force FG1. And I'm going to add those subscripts on. So R1 times FG1 times sine theta 1. I think the first thing you should always do is look at the sine theta part, because if the torque cancel, or not the sine theta part, I guess, the first thing you should do is actually look at the distance. Now, what we haven't done yet is we haven't set our axis of rotation up yet. Now, a smart thing to do would be to use our axis of rotation placement to eliminate forces that we don't know the size of. And if you look, we don't know the size right now of the normal force. That's actually what part B is, but we don't know the size of that. So how do we get around that? Why don't we set our axis of rotation right here? A, O, R. Okay? What that's going to do is it's going to eliminate these two torques for us, which we'll write down in a second. Anyways, going back to the torque from FG1, we have, let's see, R1. Let's see, this looks to be about halfway along the board. The board is 5 meters long, so that means that this must be 2.5 meters. FG1, I do know that FG1 equals M1G, which means, let's see, the child has a mass of 25 kilograms times 10 meters per second squared. So FG1 should be 250 newtons. And then sine theta 1, R would be a vector from the axis of rotation out this way. F is down like this. If we were to move this over here, we see that these are perpendicular. The sine of 90 degrees, which is the angle for perpendicular, two vectors are perpendicular to each other. Sine of 90 is 1, so this cancels out and is just 1. So we're just left with 2.5 times 250 newtons, which is easy enough to calculate. And it comes out to 625. 625 Newton meters. Okay, let's do the torque from the normal force. That would be R from the normal force times the normal force itself times sine theta. I'll put N so we know it's normal force. Again, here's where you want to look at the distance first. If you look at the distance first, you see that the distance, the displacement of that force from the axis of rotation is 0. So this torque is 0. No torque exerted. We get the same exact thing for the seesaw, the board itself. So neither of those produce a torque. I'm going to put the calculation of the torque for the 500 Newton force up here. So I'm just going to call that, I'll just call it F. TF equals RF, F sine theta. Okay. Now we don't know what RF is, but we can still come up with an expression because we do know that the force is 500 newtons. And we can make a good assumption that, let's say we're going to be pushing down perpendicularly to R. So let's say that this is 1. Okay? So therefore, the torque from this force is 500 RF. Now, let's plug this into the net torque equation. So tau net, I always do that, equals, let's see, if I were to put my axis here, this torque, if I were to pick this up and drag it, that is a, let's see, that's counterclockwise, so that's going to be my positive torque, tau FG1. And then we're going to subtract from that, because this torque would go the other way, that would be a clockwise torque. Uh-oh. I guess that pen's done. Didn't expect that to happen. Give me 1 second. Okay, hopefully this works. Okay, thank gosh. Whew. Catastrophe averted. Tau F equals I alpha. And now remember, the I alpha term is kind of like the MA term with Newton, with writing Newton's second law. I alpha, that alpha is important because we just want to suspend the child in midair. We want to hold it together and we want to hold it in place. That means we want it in rotational equilibrium, which means that there is no net torque, which means that there is no angular acceleration. So this whole term is just 0, regardless of what I is, and I'm left with this minus this equals 0. So what I'm really left with is 625 Newton meters equals 500 RF. I just divide both sides by 500, and I get 1.25 meters equals RF. Now, what does that 1.25 meters mean? Remember, it's the distance, or the displacement from the axis of rotation. We know it's got to be this side. So it's 1.25 meters from axis of rotation. We could also say, if you wanted to, that, okay, how far is it from the left edge? Because that's a pretty unambiguous thing. Well, from the left edge, it's this 2.5 meters plus another 1.25. You could also say that it's 3.75 meters from left edge. Very similar to our last problem. I'm just going to start, depending on how you want to state, or the distance or displacement from, either of those would be acceptable. Now, another question you might ask is, well, okay, what is the normal force? And there are actually 2 different ways to do this. The easiest, probably, and the one I would hope you would see and do that first, would be to just say, okay, wait, I know the size of this force, I know the size of this force, I can calculate the force of gravity on the board. All I don't know is the normal force. So based on those things, I could say, wait a second, the sum of the forces in the y direction, the only upward force is the normal force, and then I just subtract off all the downward pointing forces. Equals MAY. There is no acceleration in the y direction to this system, so this is 0. So Fn just must equal the sum of these 3 forces that are all downward. That seems pretty easy. This would be, let's see, m1g plus mb, the mass of the board, times v, plus F. So let's see, this would be 25 kilograms times 10 meters per second squared, plus, let's see, 30 kilograms, 10 meters per second squared, plus 500 newtons. 250 plus 300 plus 500. and I get a normal force of 1,050 newtons. Okay, so just because we're on a unit called torque and we're talking about all these angular variables does not mean that the original stuff doesn't work. Okay, that like just plain old forces. That's one way you can do this. There is another way that you can get this answer, and it does have to do with torque. Well, last time we set the axis of rotation up here. So remembering that since this is in rotational equilibrium, we can set the axis of rotation to be anywhere. And that's actually what we're going to do.